welcome back. This is a new unit, Unit 3, and this is 3.1, Electron Configuration. And in your textbook, it's going to be pages 136 to 145. And in your study guide, it's going to be pages 59 through 61. All right, so let's review just a little bit about the scientist's contribution to atomic. John Dalton came up with the postulates for the atomic theory back in 1803. And then shortly, maybe, 94 years later is when Thomson discovered the electron. And then Rutherford in 1911 discovered the nucleus. Then we have Niels Bohr in 1913, just 2 years after Rutherford discovered the nucleus. 1911. 2 years later, 13. And Niels Bohr said that the electrons travel around the nucleus in this orbital pattern, kind of like the planets around the sun. So it's called the planetary model. And that was believed to be the case until 13 years later, in 1926, Erwin Schrödinger used the quantum mechanics to come up with the theory that we still believe is what is happening with the electrons today. And he has these orbitals and these orbital shapes. So we're going to learn about these orbitals in this first section of Unit 3. And at S orbital, the lowest energy orbital is spherical. And then you have your p orbitals, which look like a bow tie, or these two balloons tied end on end. And they exist on the X, the Y, and the Z axis. And then you have a much more complicated orbital called the d orbital. And these are like 4 balloons tied together. And here you have 2 configurations on the x-axis. This one where it sits in line with the y. And then on this one, which is off-centered from the y. And then you have 2 that are on the z-axis, and it's these 2. This is turned so it's in line or planar with the x-axis, and this is planar with the y-axis. Then you have this really complicated one with the bow tie and then a donut around the center. We're not going to talk a whole lot about this d orbital because it's so complicated. We're going to concentrate most of our time talking about the s and the p orbital here. But Schrödinger coined the term electron cloud because he says it's in this area that an electron is likely to exist, somewhere in an area. So if we overlay all of these orbital shapes, it looks kind of like this top illustration here. So you can see that if you have all these electrons zooming around in these different separate orbitals or these balloon shapes, then it would become hazy and look like, a cloud. So let's talk about atomic orbitals. An orbital is the place in space where an electron is likely to be found. And there's 4 different types of orbitals. Okay, and those orbitals are called S, P, D, and F. S, P, D, and F. And each one of these orbitals can hold a specific number of electrons. In the s orbital, only 2 electrons can exist. In the p, 6. In the d, 10. And in the f, 14. And as I mentioned, we're not going to talk a whole lot about the d and the f orbitals. We're going to talk a little bit about the d as far as how many electrons can be held in that orbital. Hardly any on the f. I'm going to show you where the f orbital is, but that's the extent of it. We're not going to talk hardly at all about the f orbital. So we're going to concentrate most of our time in the s and p, and then just a little bit in the d orbital. That was an ugly looking star. There you go. All right. So here are the orbitals and the orbital blocks here. So it coincides with the way the periodic table is drawn and set up. So here we see this blue color. This is what's called the s block orbitals, and it's these 2 right here at the left side of the periodic table. Now you see helium is way over here. It really belongs in this S block orbital. So if we were to drag it over here and put it down, here we go. That's the S orbital. And then we have this P block. They're called blocks because they're rectangular shape because of the periodic table. The P block is right here, and it's these 6 elements, 3, 4, 5, 6, that exist on the far right-hand side of the periodic table. Then your D block elements, these are the transition elements that are right here in this center, this dropped down area that's in the middle of the periodic table. And we can see that we have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so if we go back, let's review just a little bit. S orbitals can hold 2 electrons, P orbitals 6 electrons, D orbitals 10 and 14. So if we go back and look, S orbital, 2 electrons, there's 2 columns here, 1 and 2. Okay, and then your P6, there's 6 columns here, 1, 2, 3, 4, 5, 6. Same thing with the D, there's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. How many do you think there are down here? Well, if you said 14, you'd be right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And those are the S, P, D, and F blocks. Okay? All right. And so looking at the periodic table, we also have energy levels. 1, 2, 3, 4, 5, 6, and 7. And these energy levels are what we call periods on the periodic table. Okay. So in the energy level 1, let me get my pen back. Energy level 1, we have 1 orbital, and that's just the S. Okay, now let's go back and look at the periodic table. In energy level 1, let me move my little guy here. Oops, not that one. All right, so if I move this up to energy level 1, we can see that in this red rectangular area, all we have is this S orbital. That's all we have. Okay, so let's move this down to energy level 2. All right, in energy level 2, I've got an S. And if I look over here in this red, I've also got a P. Okay, so if we look straight across like we're reading a line of a textbook or a library book, we can see that on energy level 2, straight across, we have this S here and then this P here. So if we go back to this chart, on energy level 2, we have 2 orbitals, and that's an S and a P. And these are lowercase letters. These identifiers, signifiers. Okay, so let's move this down to the level below it. Come on, let me grab it. There it is. All right, so energy level 3. Now it's going to contain your S, your P, and then a D here. So it contains 3. Okay, so energy level 3 has 3 orbitals. It's an S, a P, and a D. Okay. And we can keep going. It gets a little more complicated. Oops, went the wrong way. All right. So on this one, the 4th energy level, we have an S, a P, and a D. Again. Except On the fourth energy level, it also adds in the F. So this F, this first row of Fs, is also considered to be the fourth energy level. Even though it fits right in here, in this section right here, as far as electron configuration purposes and the energy that these electrons hold, it's also considered to be in the F orbital. Okay, that's the extent that we're going to talk about the F orbital. All right, so on the fourth energy level, we have 4, and that's the S, P, D, and the F. Okay, on the fifth energy level, we also have 4, and that's the S, P, D, and F. Okay, and I'm going to go back and show you why. Because we have 2 rows on the F orbital. So if this row is the 4th, this one is going to be the 5th. And then that's it on the F. There's no more Fs. So as we drop down to the 6th energy level, we drop off that F. We only have 3, so it's going to be an S, a P, and a D. And then on the 7th energy level, we only have 2 because this D is going to drop off. See, a D only exists in 3, 4, 5, and 6. So on the 7th energy level, we only have S and P. So on the 7th energy level, we have 2, and that's the S and the P orbital. S and P only. Okay, so that's the way the energy levels are numbered. S, this 1S, 2S, 2P, 3S, 3D, 3P, 4S, 4D, 4P. All right, so you just go straight across and read it just like a book. Okay? All right, so as far as writing electron configuration, so we're going to start learning how to write the configuration of electrons and how that's written. So we need to look at a periodic table to do this. So we're going to keep referring back to this one. So we're going to start with hydrogen. Hydrogen is the very first element, atomic number 1. It's in energy level 1. It's in the S orbital, and hydrogen just has 1 electron. So the general form that we're going to write these in is the energy level the orbital, and then the number of electrons in that orbital. All right, so hydrogen is on energy level 1. It's in the S orbital, and it has 1 electron. So that's going to be a 1, and it's written as a superscript, like an exponent. Okay, so we have energy level, that's written just as a large number. We have the orbital, and then as a superscript, we have how many electrons are there that it has. Okay, so hydrogen is said to have a 1s1 configuration. All right, so let's look at helium. Helium is also in energy level 1. Helium is right here. It's also in energy level 1. It's also part of the s orbital, but helium has 2 electrons. So its configuration is, and it shows you right here underneath, 1s2. Okay, so helium is going to be a 1s2. All right, so let's look at lithium. Lithium now is here. It's on the 2nd energy level. Lithium is 3 electrons. So when we write electron configuration, we continue writing what has been written before. The last element that's in the energy level above the one we have. So in other words, what I'm trying to say is for lithium, we have to write the full energy level that's above it. So we're going to write a 1s2, and then lithium is on 2, and it's in the s orbital, and it's the first element. So it's 2s1. The reason we do that is because lithium has 3 electrons. And if we look at these exponents, we add those up, it's going to equal the number of electrons that lithium has. So 2 and 1 is 3. So beryllium, being the next one, it's in the second energy level. It's in the s block, and it has 2 electrons. So beryllium is going to be 1s2, 2s2. Okay. Now, boron is right here. It's in a new block. So we have to write the block that comes before it, each filled block that comes before this one. So before boron, we have a 1s2. We also have a 2s2. And then we have boron, which is on 2p1. So let's go back and write that. So boron, we have a 1s2 that's filled. We have a 2s2 that's filled. And boron is in 2p, and it's in the first position. So if we add these exponents, 2, 4, and 5, that should be the atomic number of boron. Okay, and 5 right there is the atomic number of boron. Okay, so carbon is a 1s2. Carbon is 6 electrons. Okay, so we have a 1s2, 2s2, and it sets in the 2p block, and it's in the second position, 2, 4, 6. Okay, so nitrogen, it's going to be a 1s2, 2s2, 2p, 3. It sets in the third position. So nitrogen is 1, 2, third position. Okay? All right, so going straight across, oxygen. Oxygen has 8 electrons. It's 1s2, 2s2, 2p, 4. It's in the fourth position over. Okay, and if we go back and look at that, 1, 2, 3, fourth position over. Fluorine, is the fifth position over. And neon is going to be in the 6th position over. Okay, so fluorine is 1s2, 2s2, 2p. Fluorine is the 5th one over. One more than this, so it's 5. Okay, and then in the very last one, we're going to have neon. And I don't think neon I have on this page. Okay, so neon is going to be 1s2, 2s2, 2p, 6. It's in the 6th position over. Okay, now sodium. Let's look at sodium. Sodium is the first element that's in the third energy level. Okay, so it's in the spot of 3s1. See, it tells you right here. But if we're going to be consistent and write the filled orbitals that appear before sodium, then we're going to have to do, it's 1s2 because 1s2 is filled, 2s2 is filled. Now, S's have 2 electrons to be filled, so that's what the 2's are. The 2p orbital is filled, so 2p6, it holds 6 electrons. And then sodium is the 3s1. Okay, so let's go back. Sodium is in 3s1. Sodium has 11 electrons. So if we were to go count these, we should get 11. So 2 and 2 is 4, plus 6 is 10, plus 1 is 11. Okay? So what I'm going to do here is I'm going to have you pause, and I'm going to have you do the electron configurations for these 5 elements, and then start the video again and see if you got these correct. Okay, so did you get these correct? So we stopped here at magnesium, which is 3s2. So we have to write everything before it, and that's 3p1. And then silicon is 3p2. Phosphorus is 3 over on the 3p orbital, so it's 3p3. And then sulfur is all of this before it, but 3p4. Okay? Now, for those of you who need more practice, we're going to go ahead and do these: chlorine, argon, potassium, and calcium. And then I'm going to start the video again, and we'll talk about the d orbitals here: scandium, titanium, and vanadium. All right, so go ahead and pause and see if you can do these. Okay, so these are the electrons configurations through calcium. So remember, after argon, where you have 3p6, you write all of the completed orbitals before it. So this is going to jump from 3p6. Now we're starting a new energy level 4, and then potassium is in the s orbital, and it's the first element. So it's 4s1. And then for calcium, everything 4s2. All right, so let's talk about the d orbitals. So once you get to calcium here, which is 4s2, this first energy level is considered a 3d. So if we come back and pull this up, see, this energy level is considered part of the third because these electrons have lower energy than the fourth energy level. So they're low enough energy that they can be considered in the third energy level. And that can get kind of confusing. So just remember that that first d orbital is considered in the third energy level. So when we're writing the configuration for scandium, and we'll only do the first 3 elements in that first 3d orbital, because after that the electrons start switching orbitals and switching around, and it gets confusing. So we're not going to write anything past these. Now we may fill up that orbital and then go on to the 4p orbital, but I won't have you draw or write the orbitals for any of the transition metals past vanadium. All right, so this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 4s2, and then we're going to drop down to 3. It's in the d orbital, and it's the first element in the d orbital. Okay, so let's look again. 3d, right here, d, and it's the first element in that orbital. So if you can see that, that's 3d1 right there. Okay, so let me erase it so you can see 3d1. Okay, and titanium is going to be 3d2, and then vanadium is going to be 3d3. Okay, so look, I'm just going to show you what chromium does. Now, we would assume that if it's following the same pattern, this should be 3d4. 4, right? But it's not. Look, it's 3d5. So we skip the 4, and look what happens in the s orbital. It should say 4s2 here, but it doesn't. It says 4s1. So you see these electrons start jumping around after vanadium to different orbitals because of their energy that they have. So that's why I'm not going to have you write these. That's beyond the scope of this course. This is like when you get into college stuff, they make you memorize these and understand what's going on. So we're not going to do that here though. But we may fill up this entire orbital and then onto these, because all of these in the p orbital follow the same pattern that I'm teaching you now. Okay, so if we were to do scandium, it's going to have all of these. And then it's going to be 3d2. And then vanadium. Three D3. Okay. All right. So I'm going to show you here what's called the shorthand electron configuration, or sometimes it's also called the noble gas configuration. Okay. And the way that works is you take on an electron configuration, these can get really, really, really long. Because if we were doing the electron configuration for something like francium down here, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 5d10, 6p6, and then finally 7s1. That's a very long configuration. So the shorthand configuration is to look at the electron configuration or the noble gas that appears right before the element that we're writing the configuration for. Now, since all of these electron configurations are the same, see here, magnesium is the same up to this point. It's the same here for aluminum to this point. It's the same for silicon to this point. What we do is we take the last noble gas, which is neon, at the end of that period, and we write neon. We put it in squared brackets like this. And then we add on the new energy level configuration. So if I was writing the shorthand or the noble gas configuration for sodium, I would write neon in brackets. Okay, there's neon right there. And then I would add 3s1. So this is the shorthand configuration for sodium. The shorthand configuration for magnesium would be neon in brackets, just like this, and then 3s2. Okay, so if I was going to write the shorthand for, say, potassium, well, the last filled p orbital, or the noble gas that appears before potassium, right here is potassium, would be argon. Okay, so I'm going to take argon. Here it is. This is the configuration for argon. Okay, so for potassium, I would write Ar in brackets because that's the noble gas. And then I would add on 4s1. Okay, so that makes it much, much shorter than this. Okay, so if I was going to write the noble gas for vanadium down here, this, instead of writing all of this long configuration, the last noble gas is going to be right here. Okay, so that's going to be argon. So I'd write AR in brackets, and then 4s2, 3d3. Okay, so that's much shorter than writing all of this. And then by the time we get to francium, okay, so you remember I said all of that big, long configuration for francium. If we were writing the noble gas configuration for francium, I would use radon, Rn, in brackets, and then just write 7s1. All right, so just review. Just remember that when you're writing electron configuration, it's just like you're reading lines in a book. You're going to start here with the first line, read straight across. When you get to the end, what do you do in a book? You go down to the next line, read straight across. Okay? Get to the next line, read straight across. Next line, read straight across till you get to the end. Okay? And you have to write the filled orbitals that happen or that fill up before the element that you're referring to. So if we were writing the electron configuration for sulfur, we'd have to do 1s2, 2s2, because this orbital's filled, this orbital's filled, so it's 2p6. Next line, 3, this orbital's filled, so it'd be 3s2. And then we're in the orbital that sulfur is, so it's going to be 3p, 1, 2, 3, fourth one over, 3p4, right there. Okay? All right, now some other orbitals that you're going to see, some other diagrams look like this, where they have blanks. Okay, and as you go up, they're higher energy. And then here are the S, and then here are the P, S, 3p, 4s, 3d, and then 4p, because you see that these lines are the next ones you hit if you were just going up like this, and then we hit these, and then we hit the S, and then the D. So this is just another type of diagram that you're going to see. And it just corresponds with these orbitals, because see, this is an orbital, and this is considered an orbital, okay? But there's 3 of these for the P, so that's why you see 3 blanks here. Okay, so that's a blank, and that's a blank, okay? And there's just 1 for the S, so that's a blank. Okay, so on the 3D, you have blank, 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 blank. So 5 blanks here for orbitals. Okay. All right, so what you're going to see most often are these, where you have these boxes that you had to fill in, and also these boxes like this. Now, this is very simple to do. What we're going to do is just mark X's like this, and then you're going to get down to here and you mark lines like this. And we have to do this according to 3 rules. Okay, and these 3 rules are, number 1, fill the available orbital with the lowest energy level first. And this is called the Aufbau Principle. And you have to remember these, Aufbau Principle or Aufbau. And what that means is you're going to start at the bottom and you're going to fill these from the bottom up, the lowest energy levels first. Okay, so once you get to 4s, the next one is 3d and then the P. So it's just like when you're reading the periodic table straight across, it's exactly the same way. Okay, and the next rule is that if more than one orbital have the same energy level, fill an empty one first. That's Hund's rule. So here we have 3 orbitals on the P level, and each one of these orbitals can hold 2 electrons. So let's just say I had 4 electrons. on the p orbital. So this would be filled. What that means is you're going to fill each one of these orbitals with one electron before you go back and add the second one. So if we had 4, it would look like this. So we do 1, 1, 1, and then this one for 2. Okay? And then the last one, it says a maximum of 2 electrons can occupy any orbital, and that's the Pauli Exclusion Principle. So what that means is that you can't put more than 2 lines per box. So we can't do something like this, or this, or this, or this. That doesn't exist. So it's only 2 lines per box. Okay, so when we get here, this is 1 electron, this is 2 electrons. 1 electron, 2 electrons. 1 electron, 1 electron, 1 electron, then go back and add the second electron, second electron, second electron. Okay, so on this one, there's a rule that says also that electrons will spin in opposite directions in the same orbital. So when you see boxes like this, it's wanting you to indicate the electron spin. So if we just had 1 electron, you're going to put an arrow like this. For the second electron, you're going to add the arrow in the opposite direction. Now, a lot of times you'll see arrows with the triangle or the point in like this. But a lot of times when people are going fast, they don't put the other part of the arrow in. They'll just add a half an arrow like that. Okay, and that's what I do. So it looks like a weird looking 7. It just doesn't have that other side of the arrow. It's been taken off. So here we do it like this. And then 3s, 1 up, 1 down, 1 up, 1 up, 1 up. And then come back and add the down arrows like this. Okay, so if you're doing electron configuration showing the electron spins in this type of box, remember to use the directional arrows. On this type of electron configuration, all you have to do is use the lines going in opposite directions. Okay, all right, so remember those rules, write those down because you're going to have to know those rules. All right, so let's do some electron configurations for some elements, some examples. So here we have oxygen. Okay, oxygen, here's the box from the periodic table. How many electrons does oxygen have? Remember, the atomic number is the same as the electrons. So here's the atomic number. It's the same as the electrons, so this is going to have 8 electrons. All right, so if we're doing the orbital for oxygen, 8 electrons, we're going to have 1, 2, because we're starting at the bottom, okay, 3, 4. Now we're going to do the 2p. Now remember, we have to do 1 in each before we can go back and add the 7. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the diagram, this is called the diagram, electron diagram for oxygen is going to look like this. Okay, so it would be incorrect if we did, it would be incorrect if we did 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's breaking the Hund's rule, where it says we have to add 1 electron per orbital before we go back and add the second. Okay, so 5, 6, 7, 8. All right, so argon, 18 electrons right here. So we're going to have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Valence electrons. write down these definitions. All right, valence electrons are the outer shell electrons that participate in forming a bond with other elements. They're the highest energy electrons. So we're going to talk a lot about valence electrons when we start talking about bonding here. And core electrons are those non-valence electrons. They do not participate in any bonding. Okay, so let's look at an example of valence electrons. So if we do the diagram for arsenic, which has 33, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 31, 32, 33. So that's going to be the diagram for arsenic here. Now, valence electrons are the highest energy electrons that an element has. So if we look at this, the highest energy electrons are going to be just the s and p orbitals. So it's going to be these two orbitals here. So if we take this box and we put it over the valence electrons, how many valence electrons does arsenic have? 1, 2, 3, 4, 5 valence electrons. Okay, so over here on this side right here, you're going to see arsenic has 5 valence electrons. And if we look back at the periodic table, let me find the periodic table. Okay, right here, arsenic is 33. So it's right here, okay? So 5 valence electrons we said arsenic had. Look at this. I'm going to go up. It's in group 15 or 5A. So this last number, if it's a double-digit number, tells you how many valence electrons that this element has. Isn't that interesting how that periodic table works out like that? All right, so let's look at calcium. Calcium has 20 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so if the valence electrons that participate in bonding are the highest energy S and P electrons, S and P only, we're going to look at this, put our valence electron box over this. So the S and P, we have 2 valence electrons. So here it indicates 2 valence electrons. Then if we look back at a periodic table, find calcium. Calcium's right here. Oops, I didn't mean to move that. Calcium is right here. Look, calcium is in the second group. Okay, 2 valence electrons. So if we were looking at a periodic table, this doesn't apply to any of these, okay? Because these do weird things. Remember I said they do weird things. So that rule doesn't apply, or that trick doesn't apply here. It just applies to the main group elements. So if I were to ask you how many valence electrons chlorine has, right here is chlorine. It's in group 17 or 7A. It's got 7 valence electrons. How many valence electrons does aluminum have? Aluminum is in 13 or 3A. It's got 3 valence electrons. All right, so remember that trick. That's going to help you. Okay, and finally, to get wrapped up here, this is just recapping what I just said. So the general form is N indicating the energy level, S for the orbital, and then this superscript number tells you how many valence electrons are in that orbital. And if you just take the S and P and add them up, then that's going to tell you how many valence electrons that element has. Now, as far as the ions that's formed, remember an ion is any element that loses or gains electrons. Okay, the general rule is that all metals and this stair step here divides the metals and nonmetals. All metals lose electrons and all nonmetals gain electrons. There's a trend on the periodic table, and this is on your reference materials that you get. So this is going to lose one electron since it's in group 1. So it's going to be a +1 ion. The second one's going to lose 2, so it's going to be a +2 ion. And then it's +3. These don't form ions. Okay, so now we're into the nonmetals. They gain electrons. So this is going to gain 3 electrons. This will gain 2. This will gain 1. These don't gain or lose because they have 8 valence electrons, and 8 is a magic number. All elements want to have 8. So this is the trend. So if you look on your reference materials, these are the ions that are formed on these groups: +1, +2, +3, 0, -3, -2, -1. Okay, and in class, I'll go over those a little bit more. All right, so each of the following elements determine the number of valence electrons and predict the likely charge of a typical ion that might form. So we're looking at strontium. So strontium is right here. Okay, strontium has 2 valence electrons. It's a metal, so it's going to lose those 2 electrons. So if it loses 2 electrons, the charge is going to be +2. Okay, so it's got 2 valence electrons. Okay, it's going to lose those 2 because it's a metal, so it's going to have a +2 charge. All right, so that's it. Make sure that you slap that like button right across the face. Subscribe, please, and hit that notification bell so you know when I put up new videos.